see. So are folks seeing the data integration 1 tutorial right now?
Yeah, Zach, it's a little bit small. If you could make it bigger, that'd be great.
Yeah, go into presentation mode. Perfect.
Does that look better for folks?
Yep, good.
Okay, cool. All right, well, hello everyone. So Tasha and I are now going to shift gears to trying to think about how to compare ICESat-2 with other data sets. This is the first part of this tutorial. So for the most part, we're going to go over basics today. The big thing is we're going to try and read in some ICESat-2 data, both in Pandas and in X-array. And so we're also going to be looking over some of the basics of both of those packages, just to give you a better idea of how those 2 packages can help you do data analysis with ICESat-2. We're also going to be looking at a couple of other data sets to directly compare with ICESat-2. One is an airborne LiDAR, which I'll go over in more detail in a moment, and then also some Landsat imagery, just to give us some exposure with raster imagery. So yeah, let's go ahead and get started. So we have a bunch of packages that we're going to load up. Basically, these are going to help us with the analysis and also give us some nice visualization tools. And then we are going to think about what ICESat-2 data we want. So depending on what your project is, you sometimes just have to sit back and think about which ICESat-2 product you actually want. So like if you want to look over sea ice, you might want to look at ATL07. If you want to look at forests, then you might want to look at ATL08. So before you actually start doing some data integration, it is important to think about which ICESat-2 data product is important to your interests, because that can also potentially govern which other data sets you use. For these tutorials, we are going to be using ATL06, the land ice product, and we're going to be looking at Jakobshavn in particular. So we're basically looking at land ice heights over Greenland. So in order to get the data itself, we are going to be using IcePix. So we're going to import that, and we're going to specify a bunch of parameters for it for the IcePix query object. We're going to specify the ATL06 dataset. For the spatial extent, we are going to use a KML file to define the spatial bounds of Jakobshavn. We have the state range of April 2019, and we're going to specify an ICESat-2 track. Why I specify the state range and this RGT will become important in a moment when I talk about the airborne LiDAR. And then just so that we can see what this polygon looks like, I'll load this map here using the IPy leaflet package. And we get something that looks like this. And here's our polygon bounding box for the Jakobshavn region. So as you can see, the IPy leaflet gives you a nice way to just look at your region of interest. And if you want, you can easily scroll around at your leisure. You can also zoom in. After a certain point, it looks kind of gross, but you can still do it. You can also zoom out if that's your thing. So it's pretty nifty if you just want to get a good idea of what your region of interest looks like. So anyway, so we know that we're looking at Jakobshavn. So we're going to set up our IcePix query object. And we're going to use this function known as avail granules to see what ICESat-2 files we would be downloading. And sure enough, we have an ATL06 data file that comes from April 20th of 2019. Just to make sure that we actually do have data in there and it hasn't been taken over by clouds or anything, we're going to use this function known as visualize elevation, which basically calls in data from Openaltimetry and plots it on a HoloViews plot. So once we run that, we can see that we have these three ICESat-2 tracks corresponding with the 3 pairs of beams. And the right plot here shows that we do indeed have some data. So clouds aren't our enemy for this scene, which is good. All right, so now that we know that we actually have some data, we can set our Earth data credentials. I'm going to skip this step because just for the sake of time, because sometimes the data processing can take a little while. But if you're interested, then the data file of interest, that's the wrong folder, is this one right here, which is it's a processed ATL06 file basically. And that's what we're going to be working with for this tutorial. But if you want to download the data yourself, then you're free to do so. All right, so now we're going to quickly load the ICESat-2 data. Here's our ICESat-2 file. We're going to import it using H5PY, and we're going to load it in. We're going to load our the data into 2 Pandas data frames. The 2 data sets we're going to look at are the central beams, so GT2R and GT2L. And the data that we're going to put into the data frames are the latitudes, the longitudes, and the elevations, just to keep it simple. So if I load this, run this, then it'll create a data frame. And just to provide a quick visualization of what this looks like, the Pandas data frame looks something like this. It kind of looks like an Excel spreadsheet. You've got this column for latitude corresponding with this directory, longitude corresponding with this, and the ice heights, which correspond with this line right here. And we also have the indices in bold, which basically correspond to the rows. All right, so now we now have our ICESat-2 data. Next, it's time to think about what other data sets we want to use. So there's going to be a question in Slack just asking about what research problems you want to address that require more than one data set. We do provide a couple of resources for where you can look for some other data sets right here. Just for the sake of time, we're just going to provide the links and then move on. But for this application over Jakob Schaven, we're going to look at a data set known as the Airborne Topographic Mapper. It's called ATM for short, and it was flown as part of a campaign called Operation Ice Bridge. And the reason why we chose April 2019 is because this flight campaign actually took place over Jakob Schaven at that same time. And there were actually some flights that matched up with the ICESat-2 data. So that means we could potentially match both this airborne LiDAR and ICESat-2 and get a nifty little comparison between the two. We'll leave the full comparison for tomorrow, but for today, we're just going to see if we can match the ATM data with one of the ICESat-2 flight tracks. So first, we're going to load the ATM data into its own Pandas data frame. I have the data already pre-downloaded as a CSV file in the repository. And what's nice about Pandas is that you can use this function to just read in CSV files. And so if I run this cell, you can see that it basically takes that CSV file and just reads it into the frame without too many problems. So now that we have these 2 CSV files, I'm now going to switch it over to Tasha so that she can talk more about how we can manipulate data in Pandas.
Cool, thanks, Zach. Let me share this. All right, starting where he left off. I am gonna read really quickly the responses that y'all gave for research that you do with other data sets. So how to deal with tides, going from freeboard to sea ice thickness, ice surface deformation drivers, delineating mangroves, so some bio work, Yeah, not many not many research problems require only one data set. Yeah. So exploring climate grids, ice shelf lecture, and satellite drive bathymetry. Cool. So many different applications. And so hopefully what we show you here will allow you to do that. So now that we have this data in a Pandas data frame, the rest of this you can go ahead and step through with me in your code. I am going to have a live example for you to add to if you'd like in your own workbook. So you can definitely follow along that way or just follow with me. This is definitely going to be a reference for you to come back to if you need. So there's lots of information in here. So starting with this Pandas data frame, we have columns along the top that have their different variable names, and the index is here in bold. So it's kind of the structure of a Pandas data frame. It's very similar to an Excel spreadsheet. Pandas is really cool because it helps you to explore, clean, and process tabular data. And you can either pull that data into a series, which is a 1D data table, like a column, or into a data frame, which is what we have above, and that's a 2D data table. So read CSV is what Zach used to open a CSV file. It makes it very easy. This one just, nothing else is added. So Pandas just assumes a lot of the things like where the headers are and things like that. But we can do a lot of things to customize this. So here we're reading in the same data, but now we're going to add different header names, and that's going to be included here. And we're going to specify that the index column is 0. So that's going to be the UTC column. And we're going to re-specify that the header is row 0 so that it doesn't read that in as data. And so here we kind of get that with the new columns, and now we have an index with the UTC. So now we can explore the data in the data frame. If we use the .columns command, then we can look at those headers that we just looked at. If we want to look at just one column, we put that into brackets. And head gives us just the first 5 lines. You can have it put in like just the first 3 lines of your data frame just to see what it looks like. But what we can see is that the index is now added, or is also shown with the column that we asked for. So that just helps us to more easily reference it. We can do the same command slightly differently to get the same exact column output. So there's lots of ways to do that. If we want something more intuitive for our index instead of UTC, which who knows what that really means when we look at it, we can create a column of date-time objects from using the ATM file name, which I'll show you here. ATM L2, file. So this actually has the date in it. So we'll use that date with the UTC seconds of the day, combine those together to get a date time object. So here we're creating a date time, this really cool date time object that Pandas can do from that string from the file name. And then we're creating a time delta where we add to the date time we've already created, because seconds is just a difference in seconds. So we're doing a time delta using the seconds and specifying the units as seconds. And so when we add those together, we create a date time object that we put into a date time column, and then we've set that as the new index. So we've moved the UTC column over using reset index back into the data frame. And now we have this really functional datetime object as our index. And so we can easily slice by data or by date, month, and day, lots of different things. So here we're slicing the data, grabbing everything from May 6th. We can do a date range. And we can do further slicing using the .loc and iloc methods. So loc uses labels. So it uses the actual labels of each row, and iloc uses positional indexing. So if we take a look at the index, for our data frame, we can just basically copy this first one, paste it in here, and this will give us the 4 columns that had that same date time. If we want to index or slice by index and column, we put the index first, then a comma, and then the column. And if we want to do more than one column or more than one index, we put brackets around those. So these are all of the columns. And so we end up with the same index, but only the 3 columns that we were interested in. And then to do that by row and column number, we use iLoc. So this will grab the first and second row and the third, fourth, and fifth columns. So those are some easy manipulations with Pandas. We can also do some really fast and dirty statistical manipulations. So here, if we're interested in maybe taking the mean of ATM height for the entire data frame, we can do something like this, where we just add .mean and parentheses at the end, and that gives us the mean for the height. We can also use describe, which gives us a bunch of different measurements for that column. And we can take the sum of the number of measurements that we have. Those are just a few examples of different statistical manipulations you can do. We can also use group by, which is a really cool, powerful tool for grouping some of your data together. Here, we use group by on the data frame, and identify, track identifier is what we want to group the data by. So track identifier, we have 0, 1, 2, and 3. So this basically takes all of the data that has the same track identifier, groups it together, and then we've specified that we want the mean of that data. So what that ends up giving us is 4 rows. All of the data that is associated with that track identifier has been lumped together and averaged for all of the columns. So group by is really complex, but here's some documentation if you want to read more. You can do group by with multiple columns and that sort of thing. You can also resample, oops, sorry. You can also resample the data so that you can take it at different intervals using the date time object or index that we have. So there's different intervals that you can specify. You can look these up, but this is 30 seconds. So we're going to group our data by 30 seconds, take the mean of that. And now we have data that's been resampled to 30-second intervals. You can do this by month, day, lots of different things. We can, if you really want to use your own specific function, not one that Pandas has provided, we can use apply. And so apply is a function that allows us to iterate over each of the rows in the data frame, and to do it quickly. And it functions as a map function in Python, and you can add whatever function you like. So here we've added just the random numpy median function to apply to the entire data frame. And even though it's probably going to be slower than the Python version is, and then we say axis equals 0, which means this will pass in all the rows and iterate over each column, which means we'll get median for each column. So this is useful if you want to do this over the entire data frame, but usually we don't with the functions we want to pass in. So if we want to use just specific rows or columns, we can do something that's more complex. So for instance, if you want to know the total number of measurements, so number of measurements column plus the number of measurements removed, we can use a function that we've already built here that just adds two numbers together. So what we do to apply this is we use the lambda function. We do the data frame dot apply, and then lambda dot row allows us to, lets it know that it's going to iterate over rows or columns. You can write row here or X or columns or whatever is most intuitive for you. Then we specify our function and the inputs to our function. So for each row, it's going to take these two columns as A and B and perform the function. And so axis is again telling us that we're passing in columns and it's going to apply this to every single row. So this will create a new column called total measurements. That's over here at the end. So this is total measurements, which is the addition of the sum of these two right here. Cool. So I wanted to allow you guys to just get a little bit more familiar with apply. So we're going to do a quick exercise, and you'll be able to create a new column that's called distance to Jakobshavn. And this function we already have ready for you. It passes in the lat and long that we have in our data frame and measures the distance to a point along the Jakobshavn glacier ice front and spits that out. And so what I'd like you to do is take the next few minutes to finish out this dot apply line here to create this column. It'll be pretty similar to what we have up here. So I'll give you about 3 minutes to do that.
All right, so now that Tasha's given us a nice run through of how Panda works, we're going to just apply some of those basic concepts to plot the ATM and ICESat-2 tracks onto a map and just make sure that they are relatively close to each other, if not possibly overlapping. So first of all, I am going to just reset the data file using this cell. So it's back to how it was beforehand with the original headers and the indices. I'm not actually going to be using the indices much here. It's just there for reference. But what we are going to do is this track identifier refers to the relative position on the aircraft that the instrument is being fired from. So just to keep things simple, we're going to only look at track ID equals 0 because that is the track that was looking directly underneath the aircraft. Some of the other instruments were subject to a little bit of wobble just from the aircraft itself. So this just makes things a little bit easier. We're also going to change the longitudes so that they're consistent with what ICESat-2's longitudes look like. And if we do this filtering, we can see that it decreases the size of the data frame by quite a bit. The original size was about 4,200 elements. So now what we're going to do is just take all this and just plot it onto a map. We're going to first subset both of the ICESat-2 tracks based on the ATM latitudes. With Pandas, you are able to do inline index slicing, as Tasha mentioned. So these two lines are kind of nasty, but the general gist is that we are subsetting the ICESat-2 data frames to only include the data that is within the ATM latitudes, the minimum and maximum ones. Once we do that, we go back to IPy leaflets, and we use what is known as the polyline function to create these lines based on the coordinates from both the ATM and ICESat-2 tracks. So if I run this cell, it's a lot of stuff, but what it gives us is this. Just from this view, it looks like it's just two green lines overlapping with each other. But if I zoom in some, the map gets a little nasty, but we can see what looks like a green line and an orange line. The green line is one of the ICESat-2 tracks, and then the orange line is the ATM track. If I zoom in a bit more, you can see the map disappear, and you can also just barely see another green line underneath the the orange line, meaning that ATM is actually overlapping really well with one of the ICESat-2 tracks. In particular, it's actually overlapping with GT2L. That means we can actually do a pretty direct comparison between these two LiDARs just to see how well they actually match with each other. That means we can perform a bias assessment, maybe derive a time series, or any number of things. Just for the purposes of keeping time though, we'll just leave that there as a cliffhanger. And we'll look at both of those in a little more detail tomorrow. So for now, we are going to shift gears and we're going to start looking at X-ray and how we can apply that to raster imagery. And that's with Tasha again.
Great. So now we want to pair raster imagery with ICESat-2. And so we're going to talk about cloud optimized approaches for doing that, because raster imagery can get to be pretty big. Cloud optimized approaches are great because they can organize data as an aggregation of small independently retrievable objects in these file formats, or allow access to pieces of larger objects like cloud optimized geotiffs, et cetera. Today, I'll be walking through how we can use cloud optimized geotiffs or COGs, which are geotiffs files with an internal organization that enables more efficient workflow by allowing us to ask for small parts of the file that we need instead of having to open the entire image or data set. There's more information there. An example URL for a COG is here from Landsat, and the Landsat user manual is here if you want to check that out. So to start out, we want to be able to search the Landsat imagery, and to do that, we will use their STACK catalog or spatial temporal asset catalog. STACK is great because it provides a common metadata format that allows us to make easier indexing and querying of S3 buckets for geospatial data. So lots of different kinds of data can be in a STACK catalog. And so we can easily query it and look into it. To be able to access the data that we're interested in today, we're first going to set up an OS environment for the request or payer bucket, because that's where a lot of the AWS or all the AWS stuff that we have is going to be sitting. And don't worry, this isn't going to charge us. Our hub is sitting in the US West, which is where all of Landsat is. So there is no egress fees. We also will set up a similar sort of credential using Bodo, which will be passed into Raster.io to be able to get that imagery. We're first going to start by extracting the bounds from the KML file that Zach used earlier. And that's going to give us the bounds that we want to search in. So that's passed in here by west, south, east, and north coordinates into a bounding box. We're going to search this time range, which is the same as the ATM data is from. And then we're going to pass this into SAT search, which searches the STACK catalog and makes that really easy. We pass in a URL where all of that, where the STACK data is, the metadata is held. The collection that we're interested in is collection 2 for Landsat. And we also pass in the time range, the bounding box. We can pass in properties like path row or cloud coverage, that sort of constraint, but we aren't going to do that here. And then we just sort by date time. And what that gives us is a bunch of items from the STACK catalog that fit that query. And we're going to save that information to a GeoJSON file. So we're going to use it here in just a second. Yeah, so what we end up with is a SAT search item collection catalog. It has a bunch of metadata in it that you can search through, but a really nice way of looking at it could be just to pass that GeoJSON file into GeoPandas. So we get the file name or the ID for those images that fit that search, date, time, lots of different information about that. And then with those geometries at the end. And using those geometries, we can use HoloView to actually map out where those are. And so you can see that we have the path row listed here for those items. And for the purpose of this work that we're going to do here, we're mostly going to focus on the scene that's on the uppermost square, because that includes a little bit more of Jakobshavn. So from there, we want to intake this information from a catalog and read it and get it to Xarray. And one of the best way, a good way to do that is using Intakestack, which is a package for facilitating, discovering, exploring, and loading spatial temporal data sets by providing drivers for stat catalogs. So this is just providing a means to access all of that. And it's a simple toolkit for loading into Xarray. So we're going to do that here using the Openstack item collection function. And I'm just going to I'm listing out what the 6 scenes were that, or 6 files were that we grabbed from the sat search. And what this shows us here, there's actually 2 scenes, just like we saw on the map. One's level 1, one is, and the other 2 are level 2 data, so surface temperature and surface reflectance. So we're really only interested in the top one and the middle one. We're just going to look at the level 1 data because those are going to be equivalent. So taking that second scene, we're going to read that, open up that catalog item and look at the metadata to see what that looks like. So here you can see all of the information metadata for that specific catalog ID. And we can look at all the keys to see the different kinds of data that are in there. So we can look at all of these. Some of these are bands, some of these are metadata. These are what you probably recognized if you download the ICESat or the Landsat data from the website. And we can look at the metadata for each band as well from that key. So this here, the S3 is going to be the URL that we access the data from. And so there's 2 ways to retrieve that URL. This is, they're both listed here, one from the sat search catalog and one from the intake catalog, if you'd like to use it. We're also going to open and visualize using Raster IO, and we're going to use that URL to do that. And oh, somehow I didn't run this up here, these credentials, whoops. So when we run this, it'll take a second to open up that URL. But what it does is it passes in that AWS session certificate and then plots it out really quickly. And so using show, Raster IO just intuitively uses the lat longs for the or the projection coordinates for the image. It's a really easy way to visualize your data. But next we'll talk about how we feed that data into Xarray. So Pandas, just to give you a background on the differences between Pandas and Xarray, they have very similar structures. They are manipulated very similarly, but Pandas excels with 2D data tables, and Xarray is ideal for higher dimensions. And Xarray introduces labels in the forms of dimensions, coordinates, and attributes that sit on top of a Pandas-like data frame. We can get from Xarray, we can get a data array, which is one multidimensional variable with its coordinates, or a data set, which has multiple variables that share the same coordinates. And so you can kind of see that here mapped out. I'm just going to scratch the surface on what we can do with Xarray, but there's a ton of great tutorials at this site if you want to use them. So first I'll start by showing how we can open using Xarray. First we'll do it, open that item that we selected above into Raster IO or an Xarray data array. So here we can see we have one band. There's this many pixels for the X and Y coordinates. And those are listed here. You can also investigate some of these with some of these buttons. So it's a really nice layout to look at. And the difference between the data array and data set is that the data set creates this data variables section so that you can add more variables. So another way we can open that Tyler talked about earlier was Rio Xarray, which combines Raster IO and Xarray to make the opening even more efficient. And we create a data array, but now it has attributes. So Rio X-Array is just a little bit better than Raster IO on its own. And so Rio X-Array supports multi-dimensional data sets such as NetCDF. It loads CRS, transform, and no data metadata in places that are intuitive for us to look. It supports masking and scaling. It loads raster metadata into the attributes, et cetera. So it's really nice to use with X-Array. Another way that we can read in data is using Dask. And this actually uses Raster IO in the background as well. Dask is integrated with X-Array to be able to support parallel computation and streaming computation on data sets that don't fit into memory. So all of us that are using big data, this is a super useful tool. Dask provides arrays in small pieces called chunks, each of which is presumed to be small enough to fit into memory. And unlike NumPy, which when you perform a calculation on it, it does an eager evaluation, it calculates it immediately. Dask does those calculations in a lazy way. Operations that you perform on your data queue up as a series of tasks that are mapped over blocks, and no computation is performed until you actually ask the values to be computed. So if you want to map it out on your screen, if you want to look at the actual data values and calculate them, that's when the computations get done. And then that's when the data is loaded into memory and the computation proceeds block by block. So there's going to be more information on Dask in the Cloud Computing Tools tutorial. Right here, I'm going to expand on how we use X-Array using Dask. And we'll start by reading in 3 bands of Landsat using X-Array and Dask together. So again, we're going to select the one image that we're interested in. We're going to grab these 3 bands, iterating over those 3 bands. We're going to read in the data into X-Array. So for each scene, we're going to, or for the scene, we're going to grab that specific band name. We're going to read it in these size chunks. So we get to designate the chunk size that we look at. Landsat is natively in 512 by 512 chunks. So you can use 512 or multiples of that for it to be efficient. And then we specify the URL path to that scene and specify to the Dask so that it knows that it's going to be using those chunking. We tell it what the band name is for this X-Array, and then we append each band to bands. So we're appending several X-Arrays together, data arrays, and then to put this all together into one data array, we concatenate all of those. And we do it saying that the band is the dimension that we're now concatenating across. And so what that ends up doing is reading in all of these and producing a 3D X-Array. And so you can see that visualized here. We can see the attributes for all of that. And yeah, so that's pretty simple. It's nice to look at, and it'll be easy for us to manipulate. So you can read more about chunking here if you're interested in it. That's how you make this more efficient. The size of your chunks changes how efficiently you read it in and how much memory is used. So similarly with Pandas, I'll show you a little bit of what X-Array can do. We can easily explore the variables. Here we're looking at the latitude or the longitude or X coordinate. And so if you had longitude here, that would be what you have here, what reads out. And you can actually rename this. We can look at the attributes individually, and like if we want to just look at the coordinate reference system, that's there. If we want to look at one band, select just one band, we use .cell, which is synonymous with the .loc that we used before in Pandas. And so here we see we just have X and Y coordinates. We no longer have a band dimension. We can also do mathematical operations. Here, we're going to try and take the mean of that same band, but what you notice is it spits out the X-ray format. So if this is still in lazy form, it hasn't actually calculated the mean. So in order to do that, we ask for the values. And so now you can see it'll take a second because it's actually reading in the data now. And we get the average value from that band. You can also group by and do a bunch of other functions that we aren't going to show here, but it's pretty similar to Pandas. Now for the last few minutes, what I'm going to do is show you some advanced X-ray read-ins and plotting. So what we want to do now is we want to be able to create the fourth dimension of time and iterate over multiple scenes and get a bunch of bands for each of these scenes. So we're going to only pick out the level 1 data that we saw earlier. And that ends with T1, so that's how I'm selecting that, doing the same thing as we did before. Those are our scene IDs. We also now need to create a variable, a time variable to add to the X-array as we concatenate. So we're gonna take the date time information from that GeoPandas data frame that we built above and create an X-array variable called time that we'll be able to add to the data array in a moment. So that's what that looks like. So now we want to grab specific bands. We can search the stack catalog for the names of the specific bands that we're interested in. So here I have set it to look just for band names that have spatial resolution of 30 with 30 meter pixels. And so what this does is it searches through the keys, grabs the metadata and looks specifically at this information, the EO bands. GSD is the grid size data or the grid size. And I'm grabbing only the band names that have 30 meter as their GSD and appending that to band names. I'm also interested in Q8 pixel, which provides information about what our surface is made out of, if it's ocean, land, cloud, that sort of thing. And that's not actually in these keys. So I'm just adding that separately to the band names. And we can see what all the possible bands were. So this has left out the thermal data in the long wave infrared and the panchromatic. Those haven't been included in our band names. From there, we're basically doing what we did above, except for now we're adding a loop for the scene IDs. So for each scene ID, we're going to iterate over the bands, concatenate all of those bands into one data array, and then we're going to take all of the bands that are lumped together for a scene and concatenate those scenes together here, or append them and concatenate them. And we're going to tell it that the new dimension is the time dimension, and that the time indices for that are that variable that we created above. So that's going to open itself up here. And so now you can see we have a fourth dimension, time. We have 2 time steps, 9 bands. The spatial area is much larger now because we have 2 scenes that are in different locations. And what this has done is to put those coordinate systems together. It's merged them and created, and for every image that doesn't fit, each image doesn't fit all the way to the full extent, and there's NANs in those locations for each band now. So we now have those 2 scenes together. You can also use StatStack, which is a package that can do this pretty efficiently. There's some things that don't work super well with Landsat, but it works really well with Sentinel and can do this without having to do a bunch of for loops. So that's another thing that you can explore. From here, real quickly, what we'll do is we will subset the X-array and do that across time, bands, X and Y coordinates, so you can see what that looks like. Here I've selected just one time step. So we're just choosing one scene. and that's printed out here. And then I'm passing in an upper left X and Y coordinate in the projection coordinates of Landsat in the UTM 22 North, and then also doing the left or the lower right coordinates. So that has subset it there. I can show you what that looks like. So now you can see the chunks are taking up most of the square. We just have 3 bands. And we can plot just the blue band to see what that looks like after the subset. What you'll notice is that these are in the UTM projection coordinates. And what would be really nice is to actually see these in lat long, so they're more intuitive. But before we do that, what we ran into is an issue doing that in the way that Hannah and Tyler specified in their tutorial. And the reason is because, as Hannah mentioned, the coordinate systems can be labeled improperly in the data that you read in. So here ours says it's 32622. And if we actually look at the stat catalog, the CRS is actually 32623. So if we project, if we reproject without changing that information, what we end up getting is an image of actually 6 degrees off in longitude, because this is a different UTM CRS. So Jakobshavn is actually at -49. So what we actually end up having to do is to change the CRS information in our X-ray. So now it says it's 2.3, and we add this data to our, wow, that's wrong. Something went wrong there. The ATM data should plot on top of this, but this is just.
Did you redefine after you like reprojected and then you defined the CRS? Maybe you like reread in the data.
Yeah. Let's see if that fixes it. There it is. Who knows why that didn't work the first time, but now we have this Landsat image that's projected properly with the lat longs, and we can see that the ATM and ICESat-2 data is plotted on top of it. So, so all of those 3 have been added together. Congrats, we've gone over how to search for non-ICESat-2 data sets, open data and manipulate it in Pandas and X-Array, and visualize and explore it. So for, as Zach mentioned, we'll have a second tutorial tomorrow, and we'll continue on using that ICESat-2 and ATM data at Jakobshavn and integrate it with process velocity data. So great, thanks. I hope that was helpful for you.